Swayam Prabha. Digital India. Educated India.
Welcome back. So we were talking about the syntax and semantics of a propositional language, which is artificial. Let us just look back. Let us just revisit what we did. So the syntax in a nutshell, and then we'll go to the semantics of it. So first, there are the basic expressions, part of the syntax. So there are 4 names, D and J and M, as we can see, 2 one-place predicates, M and B, 2 two-place predicates, K and L, and then the formation rules, as we have seen just very briefly. If there is a one-place predicate, let's call that delta, and if alpha is a name, then delta alpha is a sentence. So for example, we have this one-place predicates. We have 2 one-place predicates. In fact, we have M and B. So M is a one-place predicate, and D is a name. So MD becomes a sentence. And then if gamma is a 2-place predicate and alpha and beta are names, then gamma alpha beta is a sentence. So we take 1 2-place predicate K, and then we write D and J. This will be a sentence also. And then we go to the logical connectives. If phi is a sentence, so is nec phi. So we take MD, we just add nec to it. This is a sentence. But if we want to do something like this, then this is not a sentence. If we add, for example, if we add this, this is a sentence, but if we added somewhere here, then this is not a sentence, right? So that is what we need to understand. So we have seen that then this also is a sentence, and if we want, we can negate it, and this will become another sentence. So this is how we make sentences, by using rule 3, and then we know that this is AND. This stands for AND. So if both phi and psi are sentences, then so is phi and psi. So you have a sentence like MD and K D comma J. That's a perfect sentence. And if you want, you can have OR here. So then that will be another sentence. And if you want, you can have if then here. Now this will mean if MD is true, then K DJ is also true. And the last one is actually a combination of, so when I write MD, both side arrow K D J, basically this is equivalent to saying that MD implies K D J, and at the same time K D J implies M D. So this is how we understand these sentences, and then we will see the semantics of each and every sentence. We now know the syntax. So when we do the semantics, we need to have the names. The names must be having some references, that is, the names must be having denotations in the real world. So for us, according to the textbook, the reference of D is Richard Nixon, N is Noam Chomsky, J John Michel, and M Muhammad Ali. And the denotation of M is a set. It is the set of all living people with mustache, and then the reference, the denotation of B, which is another 1 plus predicates. It is the set of all living people who are bald, and K, the set of all pairs of living people such that the first knows the second. So, for example, we can make our K like this. Suppose we can interpret K, we can, or rather define K. Suppose let us assume that Nixon knows Chomsky, and John knows Chomsky, and say Chomsky knows himself, and nobody knows anybody else. If that is the case, then this would be the denotation of K. So, see, you see, it's a set, it's an unordered set of ordered pairs. So, each of its members is an ordered pair, but the set itself is unordered. So, this is the most important thing to understand here. And then the denotation of L is the set of all pairs of living people such that the first loves the second. So, suppose in our system, once again we see the basic expressions, that is, we have Nixon, Chomsky, John, and Ali. So, we can have it like this. Suppose our system, our model is such that in this model only Nixon loves John and Ali loves himself, and nobody else loves anybody else. Once again, this is a set, an unordered set of ordered pairs. So, each member is once again ordered. The first one knows the first one loves the second, but the set itself is unordered. So, the semantic rules. Now, we know that every semantic rule must have a corresponding syntactic rule, and vice versa. That was the original idea. Not that all the time that can be maintained. So, yes, it is true that every syntactic rule must have a semantic counterpart, but the reverse may not always be true. In this case, in this language, it will be true, but then there will be exceptions and all that. So, we start. If delta is a 1 plus predicate, that is, delta can be either, it can either be, we have just two 1 plus predicates, it can either be M or B, and alpha a name. So, alpha can be D or J or whatever. I think, yes, our names are D, N, J, and M. Yeah, N or M. So, if that is the case, then if we have a sentence like, say, M N, and then if that is the case, then this will be 1. This will be 1 if and only if, that is, in our case this is, so this is a general thing. In our case, as I said here, delta is M and alpha is N. So, M n is 1 if and only if n, that is the denotation of n, belongs to the denotation of delta, that is in our case M. Now, for example, you interpret it this way. Suppose M n means, so M means a mustached person and a person with mustache, and then N is in our case Muhammad Ali, Noam Chomsky. So, if Noam Chomsky is a person, if Noam Chomsky has mustache, then this sentence is true. That is, if Noam Chomsky belongs to the set of people with mustache, then this sentence, that is Noam Chomsky has mustache, will be true. And in the case of 2 plus predicates, it is slightly different. So, it is very easy to see that that if in this case, for example, we have L and so this is a sentence L N and say D. So suppose this is now this is our sentence, and this will be then our gamma, and this is alpha, and this is beta. Now, if that is the case, then what will be the meaning of this? The meaning of this, or the denotation of this, will be 1 if and only if. In this case, you see Noam Chomsky loves Richard Nixon, which is not true. We can see here that the pair Chomsky-Nixon doesn't really exist. Yeah, once again, D is Richard Nixon. We just make sure, because Chomsky-Nixon does not belong to the set which is the denotation of loves. It is actually if and only if. So, the point is if it belonged to the set, then if it belonged to the set, then it would be true. But then, because it is not the case, because the truth is it does not belong to the set, the truth value of this sentence will be just 0. So, yeah. So, the same applies to other sentences. Now, we have seen that the sentence, so suppose Noam Chomsky is not a moustached person. So, the truth value of this sentence is also 0. So, that we know. So, now we have got two sentences. The truth value of this one is 0, the truth value of this one is also 0. In that case, so let us take the first sentence, that is Mn. So, if phi is this sentence Mn, then neg phi will be the sentence neg Mn, and now this says rule 3 says that if phi is a sentence, then neg phi is true if phi is not true. So, that means that we know that the truth value of this is actually is 0. So, the truth value of this sentence is actually 1, since the truth value of Mn is 0. And the truth, and then if both we take both sentences, that is Mn and L and D, both are zeros, in that case 4 gives this, that is if phi and psi are sentences, then phi and psi is true if both phi and psi are true. That is not the case. Phi and psi are not both true, because they are both false. In that case, the truth value of this sentence, that is Mn and L and D will be 0, because this is 0 and this is also 0. And so is the case with or, because in this case also at least one must be true, which is not the case. Neither is true. Now, what about the sixth sentence? We actually stopped here in the previous session. We just now catch up with our material, and we just had a small survey of the entire thing. Now, we can see what happens to a sentence like this. Now, this is something we have to see how we can understand. So, basically this is saying that phi implies psi is actually neg phi. I always confuse these two negation signs. So, neg phi or psi. Now, we need to see how this can be justified, because we haven't seen this so far. So, I will try to explain this in a simple way. I will try to do. So, you see what actually we have seen a few rules in the previous sessions, logical rules. I would like to add a few more. So, I would like to add the De Morgan rules. So, what is the De Morgan rules? We understand technically, if it is not the case that both phi and psi, then what actually is said? So, it is something like it is not the case that both I and John will be there somewhere, right? What does it mean? It means either John will not be there or I will not be there. It also will be true if neither of us is there, because the point is it will be happy if both me and John are not there, right? So precisely it means at least one is absent, or in this case this will be true if and only if at least one is false. Otherwise this falsity cannot be justified. So either, I am sorry, there is a mistake here, it should be or. So De Morgan's changes and to or, and also or to and. Now a little thinking will help us understand this rule also. I am not explaining it because it is also very intuitive. So these two laws are called De Morgan's laws, and we will apply that to some other things. Now we understand one thing. When can we say that it is not true that phi implies xi, which means suppose you are saying that it is not true that if it rains the soil gets wet. You want to deny this. When can you deny this? Suppose it is not raining and the soil is not wet. You can't prove anything. You can't prove it right. You can't also prove it wrong. Suppose it is raining and the soil is wet, but still it is not evidence against this rule, that is, if it rains the soil gets wet. Then what goes against this? What is evidence against this thing? If it rains the soil gets wet. Only one thing. When it is raining and the soil is not wet. This is the only evidence against if it rains the soil gets wet. So if it is the case that the antecedent is true, but the consequence is not true, we say that if antecedent then consequence is not true, right. So that we can very easily understand. Keeping that in mind, we can write that phi implies xi means it is not the case that phi implies psi, right. I just write double negation. I apply double negation on the first line, and then this much we want to work on. So this says that it is not the case that phi implies psi. We have just seen that this much means that phi and not psi, right. Just from what we have seen, it is the denial of any implication. Now if that is the case, then what is the next step? We apply De Morgan's to it, and then we get neg phi or neg of neg xi, right. So it is just De Morgan's, and we know that neg xi means xi. Once again the rule called double negation. So from that we can see that we can arrive at this from this in a few steps. So this is what is done. So basically we are trying to reduce if then into not and or, and that is exactly what is being done here. So if phi and xi are sentences, then phi implies xi is true if and only if either phi is false or xi is true. We understand what is being said here. So now suppose somebody says that if John has mustache, then John knows Chomsky. Suppose there is a sentence like that. So now how do we write it in our language? Basically we write something like this. We don't have a lot of space here. I'll try to erase part of it, and now we are saying that we are saying that if John has mustache, then John knows Noam Chomsky. It's a stupid sentence, but that doesn't matter. So basically, we are saying MJ implies KJN. This is our sentence. Now, what does it mean? This sentence will be true if and only if either MJ is false. This is this neg phi part when it is false, or now this is the or part, or xi is true. What is our xi? That is K J N is true. So this is what is said in this rule. So I hope we understand what is going on here. And the seventh rule is, once again, it's just a conjunction of two implications. That is, on the one hand, phi implies xi, and on the other hand, xi implies phi. So this is what we have seen in the case of an artificial language, which is very simple, but not that the human language is not that simple. We need to understand its natural counterpart. We will see how that goes. Now, L0E is a natural counterpart of the language we have just seen, and it looks like English. It's a very small English. It has a very few words and very few syntactic rules. So it's a limited English, we can say. But although it is limited, it can generate infinite sentences. So that way it is not limited. So its scope is very limited, but what it can actually generate is, in a sense, unlimited, but not that it covers all the areas of, or all the aspects of, the natural English. So, but anyway, we will see this language. So first comes, as we have seen in the natural language, in the artificial language, the first thing that comes is the syntax or the syntactic rules, and then comes the semantics of it, along with the semantic rules and everything. So we shall see how we'll understand. We need to understand this. So first, the syntax of it. There are basic expressions of these types, and then there are all. So I better write down this rule there, which is helpful for me. So that is S goes to S conj S. Neg S and NVP. When we talked about syntax, we already saw how syntactic rules actually generate. It's like an algorithm having syntactic rules. Is like having an algorithm. It can generate sentences, and then we need to see what it can generate and what it cannot generate. Remember, these are all the terminal nodes, the terminal things. So basically, this means goes to. Let us not confuse this sign, this goes to sign, and if then sign. They are different things, but we need to understand this contextually. But anyways, I don't think there is any confusion, any real confusion, but there is just an apparent confusion. We need to be careful about this. Okay, so so now this is how we can make sentences. So S goes to N VP. Now what are our sentences? What are our words? We have three names, that is Sadie, Les and Hank. We have three VIs. VIs are like 1 plus predicates. So they are in the artificial language we had 1 plus predicates, and in the natural language we have VIs. I actually stands for intransitive. So, you can see that all intransitive verbs are like 1 plus predicates. They are all 1 plus predicates. Like for example, smokes. So, smoke can just take one argument. It can just take the smoker. So, sleeps, it cannot take two arguments, but then likes or knows, these things will take two arguments, the knower and the known, the liker and the liked. So, that is how they are different, but VI is broader than the 1 plus predicates. How we shall see that? And we have 3 VTs, that is here we have loves, hates, is taller than, and then the conjuges have to be understood. So, we have just 2 conj, one is and one is or, and these are the usual and or, and then finally, it is not the case that which is a logical. So, we have these 3 logical connectives and or, and it is not the case that these 3 sentential connectives. So, this is a monadic connective neg, because it works, it gets added to one sentence, but conj works, it deals with 2 sentences. So, any conj deals with 2 sentences, as we have already seen. So, what are the sentences we can make by using this? Already we have seen while talking about the Chomskyan syntax, we already saw how sentences were made in this grammar. So, this grammar is simpler than the Chomskyan grammar we already saw. Let us just see how this grammar works. First, the syntax of it. Let us have a sentence. For example, let us just see the generation of this sentence. Sadie snores. I am just making a random sentence, or Hank loves Liz. Let us see how this sentence can be generated. So, we use the old logic that goes to logic. So, this sentence, now can you see the structure of it? So, this is one sentence, this is another one, and or is a conj. That means we have to take this root first. So, this goes to S conj S, which is a licensed root, and then this S goes to which root? This is basically Sadie snores. Sadie snores means it can take this root once again. So, that means we can have something like N and then N VP, and what can VP do? VP can go to VI, and VI can go to 3 things, either snores or sleeps or is boring. We take this root, snores root. So, I just choose snores, and N goes to, N can be either Sadie or Liz or Hank. I choose Sadie. So, Sadie snores is done. The conj, so conj goes either to and or to or. We choose or, which is perfectly fine, and then S goes to, here the S is different, right? It is not just a simple N and VP, that and then VP goes to VI, but it is complicated because it has got 2 arguments, Hank and Liz. So, we once again analyze it into N VP. We are taking this root again, S goes to N VP, and then yes, N goes to Hank without any problems, but the VP is complex because it is now this root, VP goes to VT N. So, VT N, and VT goes to loves, and N goes to Liz. So, we can see that this is a perfect sentence in our language. Now, compare this to a wrong sentence like snores Sadie, Hank or loves Liz. Can we make this sentence? We can't. This is not a grammatical sentence. Or try something like Hank Sadie snores. Now, can we make this sentence? What will be the root? we can say S goes to this is an S. So, we can say that this is an S, right. So, the entire thing is an S. We can say that S goes to N VP. Then VP, because it is Sadie Snows, now we should have then N and VP, which is not possible. No VP goes to N VP. So, this route cannot be taken, right. This route cannot be taken. So, then what is it we can do? Can we correct it? Can we do something else with this sentence? Can we do it this way? So, this will be a VP, and VP can go to VI. So, VP goes to VI, and then VI goes to Snows. Then can N be divided into N, and this will take Hank and this will take Sadie? Now, once again this is not possible, simply because there is no rule that states that N goes to say for example N goes to N. There is no such rule. That is the thing, that is the reason we can't generate this sentence. It is a bad sentence. So, similarly, if we try to make sentences, we will see that it is not possible for us to make wrong sentences by using this thing. Okay. So, so we can see that whatever sentence we can make will be a perfect sentence. So, only perfect sentences, rather, in other words, will be licensed by this semantic rule, and we understand, because we did some syntax, we can understand the generation of each sentence perfectly well. Now, we need to understand the semantic counterparts of the syntactic rules. Each rule will have a counterpart. Now, here it is not as simple as the artificial language semantics. It is slightly complicated. We shall see how we need to understand this semantics. Okay. Now, the semantic values of basic expressions, and we have seen that there are categories, right. In the previous slide we have seen that we have things like category N, category VI. So, these are the categories: conj, N, VI, VT, neg. Each category now will have its associated values and everything. First, we are looking at the category N, and there are three things there that we have seen, that it is Sadie, Les, and Hank. So, basically it is the names. So, then the semantic values of these names are here. So, Sadie, the denotation of Sadie is Anwar Sadat. Now, this Anwar Sadat, we cannot copy paste Anwar Sadat, the real person, here. That is the reason we are writing the full name, but imagine that this is the real person, Anwar Sadat. This is no name. This is a name. Sadie is a name, but this Anwar Sadat is not a name. It is a real person. So, just imagine, otherwise formal semantics will not be understood properly. So, Liz is a name, but Queen Elizabeth II is not a name. It is a real person, Queen Elizabeth II, and Hank is a name, but Henry Kissinger is once again not a name, but a real person. So, then we go to the next category VI. I have already written the category N stuff here already. Now, Snows. It is evident that from these diagrams we can see that who are the snorers, whatever is mapped to 1, right. So, Anwar Sadat is a snorer, Queen Elizabeth also is a snorer, but Kissinger is not. And sleeps, so it seems that only Anwar Sadat sleeps, nobody else sleeps. Elizabeth doesn't, Henry Kissinger doesn't. So, is boring, all three of them are boring. So, this is what the model tells us. So, suppose the world looks like this, and then we need to understand what happens. So, from this, suppose you make a sentence like Sadie snores, as we have done before. Sadie snores is a perfect sentence, or you can just add it is not that, which is neg. Suppose this is our sentence, we can make this sentence, and we can see, we will get back to this how it works. And first let us see the semantic values and category witty. We need to talk about category witty. It is because we remember that the construction of this function is a little peculiar. It does not mean that Anwar Sadat loves Anwar Sadat and Anwar Sadat loves Queen Elizabeth. This is not the direction of loving, not that this is the lover and this is the beloved. The direction actually is quite the opposite. Why is it so? Once again we look back. So, suppose we mean to say that Sadie loves Liz. This is what we want to say, right? Now, so Sadie is the lover, Liz the beloved. How is the sentence constructed? Once again, the sentence is S goes to N and VP, and VP goes to VT and N, and N goes to, now here Sadie, VT goes to loves, and N goes to Liz. This is how the sentence has been constructed. And now the problem is loves and Liz unite to make loves Liz, which is the VP here. And just a second, let us look back the rule and stuff. So, VP goes to VTN, fine. Yeah, once again we see that VP can either take this route, that is VP goes to VI directly, or it can take this route, that is VP goes to VT and N. So, now so we can see that this is how the sentence has been constructed. Then what will be the truth value? Now, Liz unites loves. So, the 2 plus predicate or the VT does not take the lover first, it takes the beloved first. According to the grammatical rule, according to the syntactic rules, it takes the beloved first. So, it takes the object first and then the subject. That is the reason the arrangement here is also like this. So, actually what we can do, we shall see the calculation of it. At that time we will try to understand how it actually works, but this is just here I wanted to mention what was happening, just just that much. I just wanted to say that I just need some space here. Okay, so we go to the next slide. Here is the meaning of hates, similar things. So, this is not a hater, this is not the hater, this is actually a person hated, and here is the list of haters. So, actually this list somehow means that Anwar Sadat hates him, Anwar Sadat does not hate himself, Elizabeth does not hate Anwar Sadat, Henry does not hate Anwar, but yes, Anwar hates Elizabeth, because this is one. It is not Elizabeth hates Anwar, it is this direction. Always we need to understand that for the 2 place predicates, or in our case the VT, this is the direction, this is the direction, it is all the time this, it is not. So, this is not the direction for here also, and then is taller than, and finally the category conj, that is conjunction. We have to just and or. We can see that 1 makes 1, that is if true truth values, when 2 truth values come, we can have another truth value by having and. So, for example, you have this construction phi and xi, then if phi gives you 1 and xi gives you 1, then only and will make it 1. So, if phi is 1 and xi is 0, you get 0, and then 0 1 also once again gives you 0, and 0 0 definitely gives you 0. This is from the very meaning of AND. So when I say both Tom and John are I don't know, are linguists, I am saying that both sentences are true. It will not be true if one of them, if either of them is not a linguist, right. So in order for this sentence to be true, both the sentences must be true. We have seen that. So if one is not true, like this or like this or like this, here both are false, in this case definitely we get a false sentence. And or is just the opposite. So so if at least one is true, so when you have phi or xi, if at least one is true, so suppose phi is true or xi is true or both are true, both also is a case of at least one, right. So in all these cases or will be 1, but when neither is true, it has to be false. So and neg, it is just, you know, as we know that it's a it works, it's a monadic operator, it works on one sentence and it just changes the truth value of that very sentence and nothing else. So when we have a sentence like Sadie snores, and if we add, it is not the case that to that sentence the meaning will be, so what will be the denotation of that? So it will just change the truth value of it. If Sadie snores is a true sentence, then it is not the case that Sadie snores will be a false sentence and vice versa. So we know that, but this is informal, we need to see the rules and then we get back to all these constructions and everything. We'll do that. The semantic rules. Now first, if alpha is a node, and if alpha looks like beta goes to gamma goes to beta, where gamma is any lexical category and beta any lexical item, then gamma goes to beta is a syntactic, and if gamma goes to beta is a syntactic rule, then the value of alpha is the value of beta. So actually it's a very simple thing, it's not complicated. So basically it is saying that, suppose, so what is a lexical item? A lexical item is the last thing, it's the end of the branch. So for example, we deal with once again a very simple sentence, say for example Sadie loves Hank. We do not know whether this is true or not, but the construction is n and Vp. Now Vp goes to Vt and n, and this n goes to Sadie, this Vt goes to loves, and this n goes to Hank. So this is how the sentence is constructed, and in this case, now suppose, so these are the lexical items. This is a lexical item. All three, each of these three is actually a lexical item, but these are lexical categories. So any non-terminal node is a category. So n is a category, Vp is a category, Vt is a category, once again n is a category, but these are items. Items are real words that actually constitute the language, the natural language. Okay. Now so the rule says that let us concentrate on just one area, just this area. So n goes to Hank. We know that Hank is a lexical item and n is a lexical category. Let us see what happens in this case. So the rule says that if alpha is this node, that is alpha is this branch, alpha is neither n nor Hank, nor the connection between the two, but alpha is the entire node, that is n goes to Hank. If this is the case, then what happens is something like this. If this is the case, then, and you see n is evidently gamma and Hank is beta, and alpha is the whole node. So basically alpha is the node, that is gamma goes to beta. This node, this entire node is alpha. What then will be the truth value of alpha? You see here, it completely ignores the truth value of n, because after all, what is the truth value of n? N will collect its truth value from the item. Any category finally has to collect its truth value from the item, because categories are not assigned any truth value, only items are assigned truth values. Hank basically has a truth value which is Henry Kissinger, not truth value, I am sorry, denotation. So, yeah, I just correct all my sentences, replace truth value by denotation. So, I just wanted to say that every category collects its denotation, its reference from the item associated with it, right, because n is never assigned a truth value. If you just reference, if you see the construction of it. So, category n, so category n does not have a truth value, but things that belong to category n will have truth values. So, references, I am making mistakes several times. So, for example, Sadie being an element of the category n has the reference Anwar Sadat, and Liz, the same applies to everything. Now, look at category Vi. Category Vi as such does not have any reference, but then the members of VR, that is snores or sleeps or is boring, would have references. So, for example, the reference for snores is this function where Anwar said that it is mapped to 1, Elizabeth is mapped to 1, and Henry is mapped to 0. So, yeah, so that is the point. So, no category has any reference of its own, but the member of the category, the thing that is associated, the lexical item that is associated with the category will have a truth value. So, Hank has the truth value Henry Kissinger, reference Henry Kissinger. So, then that reference will be pushed up in a sense, and that reference will be eventually the reference of n, category n. That is the reason the reference of alpha is just the reference of beta. So, what is beta in our case? Hank. So, precisely they are saying that what is the reference of this branch? That is n goes to Hank. The reference of this branch is actually the reference of Hank. So, the reference of the entire branch is Henry, or in short, as we have seen, we can use this abbreviated form HK, right, Henry Kissinger. So, HK. So, HK will be then the reference of the entire branch, this branch, right, the entire branch. Now, similarly, so this is one thing. Let us calculate the truth value of this VP finally, we will see that. So, everywhere similarly, let us consider this branch, that is Witty goes to loves. What is the truth value of it? The truth value once again will be, I am saying truth value in the place of reference every time. So, I think you may correct me when you listen to this. So, once again look at the entire branch, Witty goes to loves, and Witty, which is a category, does not have any reference of its own. It will collect the denotation of the terminal item or of the lexical item loves. So, this in this case is alpha, and this in this case is beta. Gamma once again does not play a role in determining the reference of it, because it does not have a reference of its own. So, we have 3 branches like this here, where the last thing is a lexical item. So, that is, one is this n goes to Sadie, Witty goes to loves, and n goes to Hank. This branch is different. This branching, for example, VP goes to Witty is very different, because here nothing is going to a lexical item. So, here a lexical category VP is going to another lexical category VT. So, this case will not be covered by this rule. This rule will cover just 3 things, that is, it will cover I just want to clear a bit of space. So, this will cover basically this branch, and this branch. So, according to this rule, the truth value of this branch, this entire branch, that is n goes to SADI, will be, as we have seen, the reference of SADI, which is actually AS, and the truth value of VT goes to love. Sorry, the reference, not the truth value, is the reference of loves, which is this huge function, which is given somewhere here. Yes, it is actually given here. So, this entire thing will be the truth value of that means this thing will be the truth value of this branch VT goes to loves, and then the truth the reference of n goes to Hank will actually be the reference of Hank, which is Henry Kissinger, right. So, so this rule covers just these 3 cases, that is n goes to SADI, 1, 2 and 3. Other branches are not covered by this. So, the point is, whenever you have an item, the truth value of the item will travel up, and that will reach here, that will reach here. So, it is actually a mechanism to push the references up, and we shall see how it works in other cases also, because this, as I said, this does not cover all cases. So, then the rules, these rules look very complicated, but they are not as complicated as they look. So, you see that if alpha is a VP goes to beta, we can consider the old one, or we can consider bigger sentence. We can consider a sentence like S goes to Sadie snows, or Hank loves Liz. Let us take this, because we have lot of space for working on it. Then once again Sadie snows. So, we need to replace these sentences, because it goes to, these are not the terminal things, this is the sentence. So, just I will take a second. Yeah. So, we have just this rule where we know that S can go to 3 options. So, one is the conj option. So, basically this is S goes to S conj S, and then this S goes to N and VP, VP goes to VI, and VI goes to snows, and N goes to Sadie, and conj goes to or. We are constructing the old sentence we wrote here, and then this S goes to N and VP, where the VP goes to VT and N, VT goes to loves, N goes to les, and this N goes to Sadie, say. So, okay, this is our sent. It's a little strange, little odd, because when you say Sadie snows, or so if you want to say this in a natural situation, you would say that Sadie snows or he loves Les. you would not say Sadie loves Liz, but unfortunately we do not have he or she or anything here, so we just write it like this. Now once again we do the calculation here. Now this is about VP goes to beta, and what is it? Beta is Vi goes to something. So basically it is talking about this branch. It is talking actually about this branch where VP goes to Vi, right. So here alpha is this VP goes to, so alpha is this whole branch, alpha is VP goes to beta, and we can see that beta is actually Vi goes to something, that something is represented by this triangle. It can be anything, in this case it is nose. Then once again you see that the reference is being pushed up, right. So what was the reference of this? This is covered by the previous rule. Now if this branch is alpha 1 and if this branch is alpha 2, then we can see the difference. Basically what is the reference of alpha 1? This will be pushed up, so it will basically be snores, right. And then what is the reference of alpha 2? Alpha 2 is basically VP goes to Vi, VP goes to beta, which is Vi. Now alpha 2, the reference of that is actually the reference of beta. What is our beta? Already beta has got here, already there is a reference. What is it? Snores is pushed up already, so it has reached here somehow. So now beta is not just so what is the reference of beta? Already it is this thing. So actually this is our beta, and the that is actually beta is our alpha 1, right. This entire thing is beta. So then it is already snores, we know. So the reference of alpha 2 then will be once again snores, because already it has travelled up. So yeah, so snores travels, not snows, actually the truth value of it, sorry, the reference of it has already travelled from here to there and then to there. So this is the travelling path, right. And then if this is the case, what we get? So then in this case, what is the, so snores actually has come till here. So the reference of snores has already come here, right. So yeah, so then we can see that the entire node called alpha 2 has got snores, right. And similarly this will be covered by the first rule, and if so what is it? Basically the reference of this branch is nothing but Sadie. So here under this you have something like this, not that n has got a reference and VP has got a reference, but the entire branch called n goes to Sadie has got a reference, and the entire branch VP goes to Vi, that goes to snores, has got a reference. What are those? We know that those are Sadie and this is snores. We know this already, that they have travelled up, and we have a thing like this. So then the truth value of S will be calculated on the basis of that in the next session. Thank you.